Okay, so what does generalization look like across double-base smokeless powders? Or at least a double-base smokeless powder to various sort of renditions of different items that have similar sort of chemical properties and or different kinds of smokeless powder. So in this case, we trained dogs in a small sample here to detect double-base smokeless powder using one of our olfactometer setups, which is in this room. So basically what we have here are 3 different olfactometers, which are basically boxes that can present any of, depending on the model, 6 to 18 different odors to one of these ports. So the computer just controls which odor goes to which port. We have a panel that goes up and down via an automated system, which you've seen before in some of our other lectures. But basically, the dog is trained to indicate which of the 3 ports has the target odor in it. We train the dogs on an intermittent schedule of reinforcement in which 60% of correct responses were reinforced. So thinking back to our schedules of reinforcement, right? So our intermittent schedule means that we did not reinforce every correct response. And on average, it was going to be 2/3 of responses were reinforced. Or specifically, it was 60%. Each correct response had a 60% probability of reinforcement. So in this case, if a dog did make a correct response, there was only a 60% probability that the terminal reinforcer was going to be delivered. And the purpose of this was to build a bit of resistance to extinction so that we would be able to present a variety of different odors under extinction. Remember how the generalization gradient tests are done under extinction so that you can make sure that you're not training the dog to the different tests or test stimuli that you're trying to probe. So if they responded to an odor, say smokeless powder or a variation of smokeless powder, there was still a probability that they were not going to get a reinforcer. So it made it more difficult to discriminate the contingencies between smokeless powder and related smokeless powder odors, whether they were going to get reinforced or not. Dogs were tested in 40 trial sessions. There were 8 blank trials, in which there was no target odor present in any of the containers or any samples that we were testing. They were just distractor odors purely to make sure that they would not just respond to any novel odor. There were 24 trials with the target odor. Not all of them were reinforced. Then we had 8 non-reinforced probe trials where we would put in an odor of interest, so an odor that we wanted to assess generalization to. And if the dog alerted to it, they didn't get reinforced, which was based off of the intermittent schedule of reinforcement. So if they responded to smokeless powder, there was only a 60% probability of reinforcement. If it was a non-target, they didn't get reinforced. And if they responded to a distractor, they also did not get reinforced on that. So what did it look like? All right, put the delay there.
Search.
Buster searching. And when he sits here and holds for 3 seconds in the response, that would be a correct response. And all clear.
Search.
Would be inserting the nose in all 3, and then pulling their nose outside of that. So we were measuring both how long they kept their nose inside by latency or by the infrared beams that were in front of the ports, measure how long they hold their nose inside of that, so that we can measure how long they keep their nose in there and also their probability of a response. So we had a variety of different odors that we were interested in this case. So we had smokeless powder, which was the trained target that they were responding to about 98% of the time. Then we had a couple of things that were in contact with smokeless powder for a 48-hour period of time. We had a t-shirt material. We had a gauze material that was in non-contact with the smokeless powder. It was basically set above the smokeless powder in a container with sort of a stainless steel grid over the smokeless powder. Sorry, I can't see. So we had smokeless powder, stainless steel grid, and then the material will sit on top of that. And then that sat for a 48-hour period of time. And we found that that generated really high response rates to that at about the similar rate to the actual smokeless powder itself. We used a couple of different materials like the Gaxen tubes. If it had direct contact with smokeless powder, we got good responses to. If it was done non-contact, similar to the cotton or the gauze, we saw a bit of a decrease of response. So that it was responding about 60% of the time. We packed up PVC full of smokeless powder, sealed that up, and then put different electronics in it. We had about a 60% hit rate to that. Single base smokeless powder, we had about a 55% response rate to that. Bullets, a clean gun, control gauze, DPA, which is diphenylamine, which is the primary volatile from smokeless powder. If you were to essentially use a GC mass spec to look at what are the actual chemicals coming off of the smokeless powder, this is the most common one that's coming off of it. So that indicates that the dogs are not just simply detecting the chemical that is most prevalent in the headspace, because they showed very little response rates to that. We had a fired gun, benzaldehyde smells like almonds. This was an arbitrary control test. Our control IED, to compare that to the one that had the smokeless powder in it, indicates that the dogs weren't just alerting to the PVC or the electronics, that they were specifically alerting to the smokeless powder that was inside of it, and then the control t-shirt. So we weren't really able, remember how we talked about the generalization gradients. We can't make a generalization gradient where we have a single stimulus on here because there's no particular way to line up these different stimuli. We purposefully lined them up, so it went from highest to lowest, but there isn't like a wavelength of light or a value of 1, 2, 3, 4 to give any of these. So because of that, we can't quite make the same generalization gradients that I was talking about, but we can look at how much generalization do we get to different variations of the odor of interest. And statistically, what we found is that the single base smokeless powder was significantly lower than the actual smokeless powder in of itself. But we can also look at their nose hold time. So the dogs were trained to hold their nose in the port for 4 seconds for a correct response. And we can look at what the average nose hold time was in total. If the dogs were unsure and they sort of took their nose out, put their nose back in, shook it all about, did the hokey pokey and did it all over again, we were counting all of those times so we could get a sense of how certain or uncertain, I guess, if you will, of poking their nose in, holding it in versus taking it out, going back and double checking. In that sense, was all going to be sort of increasing the total sniff time. And from that, what we can see is, again, non-contact shirts and non-contact gauze were very good at capturing and having the dogs indicate that it smelled like smokeless powder. The direct contact Gaxen also had a very, very strong response of around 4 seconds. The single base smokeless powder, remember, this only had a 55% alert rate, but they did hold their nose in for about 3.5 seconds, indicating that, at least in this case, they found it of substantial interest, but not quite enough to alert most of the time. They would be like, it's close, and then pull their nose out and not actually make that sort of, at least in this case, the train final response of a 4-second nose alert. Similar response to the IED, and then to the non-contact gauze. And then for all of the other stimuli was substantially lower. The bullets, the DPA, again, the DPA was quite low, of only about 1.5 seconds. A little bit higher than what our like benzaldehyde and some of our controls were, indicating a little bit of elevated interest in it, so that there was something there, but definitely not enough to really change or be quite indicative of the different items that actually contain the smokeless powder. So again, we can't really create that generalization gradient that we saw before because odors don't really have a very straightforward generalization gradient to align things by, except in a couple of very specific situations. But we were at least able to align them based off of which ones they showed more or less generalization to. And this allows us to look at, well, how related are certain odors to the targets that we've trained the dogs, and will they spontaneously respond to these variations of a trained stimulus? And in this case, we had substantial interest for single base smokeless powder after the double base smokeless powder, but the actual alert rates only led to about a 55% response rate, indicating that probably the single base smokeless powder, like we talked about before with that generalization gradient, probably would need explicit training too. So basically making it another S+ in that generalization gradient to try and broaden that generalization gradient out a little bit so that they respond to these variations of that target. As I sort of indicated before, there's also important impacts of training different kinds of S minuses or S deltas, or extinction stimuli. So going back to our pigeon example, so say for example, we trained our pigeon to this kind of brownish color, SD, and we reinforce all responses to that. We get our nice generalization curve that we saw before, where all of the responses are to this particular color of that stimulus. And again, this is an example of the different wavelengths of light. So with wavelengths of light, we have a very clear stimulus that we can just align up on our x-axis, where we can't really do that with different odors, but we can get a very nice, 500, 510, 530, 520, 540, 500, and just have a very clear numerical sort of x-axis here. But say, for example, we take another stimulus that's kind of different, but relatively similar looking, and make this our S delta, and we don't get reinforced for that. What ends up happening with sort of this is our S delta being trained, so here's our original one, here's our original curve. Now we add this stimulus here as an S delta, or a extinction stimulus. We get a phenomenon called peak shift. And what this peak shift does is that the animal was originally responding most to their trained stimulus. But after training with this extinction stimulus of an S delta, the entire generalization gradient shifts away from the S delta. And now the highest level of responding is no longer to the 520 nanometers. It is in this 525 range. It's actually something further away and not the actually trained target. And in fact, the trained target gets a substantially lower, or there's a substantial decrease of responding to this very specific trained target, interestingly enough. And that is because we are getting a substantial pull from this extinction stimulus to have no responding here. So then it shifts all of the high levels of responding to something further away from the actual trained stimulus. And this is data from actual pigeons of one of the original experiments that looked at this. So here is our control. We trained them to one target here at our SD at 550 nanometers of light. And then we put different extinction stimuli here, here, and here, looking at different groups. And what you can see is that you actually get a shift away of responding from the trained target. So here's the trained target. And in many of these cases, there's actually less responding to the trained target than to examples that are actually further away from the trained target in of itself. So if we have an extinction stimulus that is out here, so looking at this sort of, we'll look at this little dashed line at 590 nanometers, which would be right here. We have a shift of this peak so that the peak of responding is actually occurring at around 540 nanometers. Then if we train something at like 555, which would look like this, we have very little responding at the 555. They don't have much responding at the actual trained SD stimulus, and they show more responding to things substantially further away in around the 530 nanometers of light range. So we basically shifted from 550 of their peak of responses to 530 by just training them not to respond to 555, 560, 570, etc. So this is the example of peak shift. So the definition of peak shift is a shift that occurs in the peak of a generalization gradient away from an extinction stimulus. That is that peak shift. Both experienced SDs and experienced S deltas can affect generalization gradients, which indicate that there is importance for relative stimulus control, meaning that your experience with what are your target stimuli and what are your extinction stimuli and how closely they relate to each other have very important impacts on the range of stimuli that you respond to. So in this case, if you had multiple SDs and multiple S deltas, that shapes this generalization gradient and can be in desirable ways, or perhaps could be in undesirable ways with this sort of peak shift phenomenon. So what is a potential application of this peak shift phenomenon or these generalization gradients? So as I said, there are very few examples that we can use with odors that demonstrate these kind of effects. However, there is one situation in which we can do that, and that is going to be by manipulating the concentration of an odor that we want the dog to respond to. So we did some prior research on this. This is an example of a setup that we had that was a no-go, no-go task. So here the dog is trained to insert their nose into the odor port, sample if the odor is present or not. If the odor is present, they're trained to either hold their nose in the port or press a little lever over here to indicate that the target odor is present. And if it's not present, they have to remove their nose from the port and not press the lever during that period of time. So the question we had is that if you train the dog to a single concentration, one, what range of concentrations will they spontaneously generalize to or spontaneously respond to without any reinforcement? And then secondly, can you actually train an extinction stimulus to a concentration that they did respond to, and how would that then change their responding? So here's an example. Sticks his nose in, indicates that the target odor is present, and then starts pressing the lever to indicate that the odor is present. Or they stick their nose in and indicate that the target odor is not or present there by holding their nose and wagging the tail. So what did we actually get? So initially we trained the dogs to this concentration of the odor here. So a 0.01 dilution of our target odor, which is basically a 1% dilution. And we looked at response rate to a variety of different concentrations related to that spontaneously. So these were tested under extinction. So the dogs were not reinforced for any of these concentrations, and we wanted to see which ones they responded to and which ones they didn't. So statistically, at least better than chance, or at least better than the response probability, they responded to all of the odors from this value down to this value, the 0.0025. So about a 10-fold range would sort of indicated the range that the dogs would respond to. So it was a relatively narrow range, and it did indicate that concentration did have a relatively important impact on the probability of response to that target odor, which we'll be talking about in a couple of other studies, the potential importance of concentration as being a stimulus dimension that we need to explicitly train for. Because if we explicitly train, remember, here, 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 we might get a much broader generalization gradient than what we kind of see here. And we only tested the lower half of concentrations, not the higher half of concentrations for time purposes, but presumably something somewhat similar would have been observed on the higher range of concentrations. But we were specifically for this study interested in the lower ranges of concentrations. So we found within this situation, the dogs would go about 10-fold lower without explicit training, but does suggest that if we wanted them to go lower, they would need explicit training. So then our next question is could we pick this stimulus that the dogs did respond to at least 25% of the time, and then purposefully make this an extinction stimulus? And then what would we expect to happen? We would expect that this would go down here, and that a lot of these responses would go down closer to zero, and perhaps the responding here is going to be lower than what we saw previously because we were getting ultimately a shift towards responding to higher concentrations. What we found is that we could definitely train the dogs not to respond to the 0.0025 concentration. And what we found is that when we tested the dogs a second time, after we trained them not to respond to the 0.0025 concentration, they actually showed the exact same generalization gradient. There was no real difference. So then what we thought is, well, maybe that's because it was happening in different sessions. So if within the same session, they were getting extinction stimuli trials to this 0.0025, while being reinforced to this 0.0001, we did see the sort of generalization gradient kind of change, where we got decreased responding here, and then we had lower responding to our actual target rate. Presumably, if we went to the higher concentrations, we would have seen the peak over here somewhere to a much higher concentration than to what we explicitly trained. But we did find that we can have get relative stimulus control by making sure that we were presenting the 0.0025 as an extinction stimulus within the sessions, and the 0.01 as a reinforced target odor. And we would get declines in responses for these concentrations or across all of these concentrations when that occurred. So to answer, if you train a dog to a single concentration of an odorant, what range will they respond to? It was about 10-fold lower than what that training target happened to be. And can you train the dog to, and this is actually, sorry, close to what has been demonstrated with rodent generalization and concentration as well. And can you train the dog to not alert to a concentration it would otherwise alert to? And the answer seems to be yes, within the context of continuous discrimination training. So what this does imply is that if you have continuous discrimination training, dogs can learn to not alert to a detectable but lower concentration of that odor that's even just within 10-fold of their training target. So where would this be potentially, important is that if you want a dog to alert to low concentrations of an odor, and you have your environment is not clean, meaning that there's potentially residual odor in different environments, what can happen is, say, for example, you're running a training session and you have a residual odor concentration that is at this 0.0025 level, but you don't know about it because you left it there yesterday, removed the item this morning, and there still seems to be a residual and the dog is responding here. So you put it under extinction. You wait the dog out, you don't reinforce them, and then you wait until they go to their correct train target stimulus and they respond here. What you can be doing in that training is that you're explicitly training them not to alert to the lower concentrations, which they clearly will make that separation. So instead of responding at this rate, they will go down to near zero levels of response rate and basically be suppressing responding to low concentrations, and pretty much this entire range of concentrations where the dogs would actually have been in a 60 to 70% probability of responding, they're actually at about a 10 to 15% probability of responding because of this extinction training to potentially residual concentrations that you didn't realize. So what this highlights is that it can be really important, or the dogs can be very sensitive to ranges of concentration of the target, and that residual levels, if they can still detect it and show responses to that we then extinguish, can be behaviorally relevant and lead to changes in their generalization gradient of what concentrations they would respond to. All right, so now we're going to take another quick break because I think that was kind of extensive, and get on to the next topic.